Hello everyone, welcome to my YouTube channel Electrical Engineering. This is lecture number 1 belonging to lecture series on questions and answers in transformer. So in this lecture number 1 which is belonging to lecture series in questions and answers in transformer, we would draw the connection diagram for a 3-phase transformer which is named as DY11. So we will begin step by step. What is the meaning of this thing DY11? Here D is written in capital letter. So capital letter means it is belonging to high voltage side. So this is belonging to high voltage side. So we should remember that if it is written in capital letter, here you can see D is written in capital letter, capital D. So it is belonging to high voltage side. Likewise we have Y which is written in small case letter. So since Y is written in small case letter, so it should belong to low voltage side. So it is belonging to low voltage side. And we can see digit 11 is written. So here digit 11 means that it is 11 o'clock. Time is 11 o'clock. Now it is a interesting method of designating the phase difference between the line to line voltage on the high voltage and low voltage side in terms of the clock method of angle designation. Here what we do, we actually denote the phase difference between low voltage and high voltage side of the transformer in terms of time in the clock. Now here I would like to mention that we are actually signifying the phase difference between line voltage on high voltage side and line voltage on low voltage side. So we will be actually focusing on the line voltage. So line voltage of HV side and your line voltage of LV side. So this is what we are focusing here, line voltage of HV and LV side. Now what is the meaning of 11 o'clock? We already know actually, it is needless to say, and we all know what is the meaning of 11 o'clock. So when we are saying the time is 11 o'clock, let me draw a clock so that we can relate it in a better way. Let's say this is your clock. So if we just mark it on the clock side, let's say this is 12th position, then at angle of 30 degree we will have 1 o'clock position, then another 30 degree later we have 2 o'clock, then 3 o'clock, then here we have 4 o'clock, 5 o'clock, 6 o'clock, 7 o'clock, 8 o'clock, 9, then we have 10 o'clock, then 11 o'clock. So the time is basically 11 o'clock. We can see here what's the time in the clock, it's 11 o'clock. So let us do one thing, let us place it here, the minute hand. Since it is 11 o'clock, so minute hand will be pointing towards 12 and the hour hand will be pointing towards 11. So hour hand is pointing towards 11. So this is my hour hand. So this is hour hand, it is representing the LV side line EMF, right? So this thing is your hour hand of the clock, hour hand of the clock, and it denotes, it is denoting, or you can say it is representing, whatever word you use, it is denoting LV side line EMF. It is denoting LV side line EMF. LV side line EMF. Now you can also say LV side line voltage. So this is your hour hand. Then we have here 12 o'clock position. So minute hand is at 12 hand. Sorry, the minute hand is pointing towards 12. So this thing is your minute hand. This thing is your minute hand, and this minute hand of clock is basically representing the, it is representing or denoting, it is denoting HV side, that means high voltage side line EMF, high voltage side line EMF. Now I would like to mention that in this convention, which is your clock method of convention, and this convention is used to denote the phase difference between the line to line voltage of a three-phase transformer on the HV and LV side. So we are simply saying that the high voltage side is delta connected because it is written in capital D. The low voltage side is star connected because it is written Y. You know that if you invert the star connection, let's say the star connection is looking like this. Let me draw it properly. This is what is your star connection. So if you invert this star connection, it will look like a Y. So usually we call this Y connection as the star connection. So Y is written in small case letter. So small case letter means it is belonging to low voltage side, LV side, and 11 means that there is a phase difference of 30 degree between line to line voltage on HV side and LV side. So 30 degree is the phase difference between the line to line voltage on HV and LV side. You know that this angle will be your 30 degree, this angle is 30 degree. So we intend to draw this connection for a three-phase transformer which is having this nomenclature DY11. So we have to remember one particular thing is that in this clock method of angle designation, this is very important. I am writing in a different color. Let me write it. The minute hand is always fixed at, minute hand is always fixed at 12 o'clock position. So this is something which is not obviously there in actual clock. It is deviating from the actual clock behavior. In an actual clock, obviously minute hand is also rotating, the hour hand is also rotating, the speed being difference, the second hand is also there, which is not shown because we hardly use in our day-to-day life the second hand. I mean to say, when we are saying somebody any time or like that, we usually say the hour and minute. We don't care about saying the second. So maybe you can ignore the second hand. So we have only here two hands of the clock. The two hands of the clock are minute hand and hour hand. Now there is a simple correlation. If you figure it out, minute hand is longer in length. Minute hand is longer in length. So it is denoting the high voltage side line EMF. On the other hand, hour hand is shorter in length. So it is denoting the line voltage of the LV side. That means the low voltage side. And one particular thing we should not forget is that minute hand is always fixed to 12 o'clock position. However, the hour hand is free to rotate. So this is also another thing. You are free to rotate the hour hand. So we are saying, however, the hour hand is free to rotate. The hour hand is free to rotate. So it can rotate any position. It is hour hand is free to rotate. It can rotate to any position, but the minute hand is always fixed at 12 o'clock position. So let me just take you to this drawing which I have made. So you can see these are the 12 divisions on the clock, and here each division will be obviously 30 degree, because you have 12 divisions and a circle means 360 degree. So 360 by 12 is your 30 degree. Now let me then take you to this particular diagram. You can see here 11 o'clock position is shown. So this is belonging to L.V side, low voltage side, line EMF, low voltage side line EMF, and this is belonging to high voltage side, line EMF. This is belonging to high voltage side line EMF. Further, we have mentioned again earlier, I have mentioned, again I am mentioning, minute hand is always fixed. Minute hand is fixed. It is not free to rotate, fixed at 12 position, 12 o'clock position. Now let us begin the drawing. So in order to build the drawing, let us do one thing. Let us first write A, B, C as if they are the vertices of an equilateral triangle. As if they are the vertices of an equilateral triangle. So we are doing that. I am writing here terminal A2, terminal B2, terminal C2. So I have I have taken 3 vertices. Let's say this is your A2. Then so I have started writing from the top position, that means the vertex position. What we are doing, we are going to start with the connection diagram for DY11. So since D is written in capital letters, so it is belonging to high voltage side. So we are writing A2, B2, C2. So you see I have started from the top position, that means the vertex position. Then I have moved in the clockwise direction B2, then C2. So since it is your high voltage side, so you can observe the terminals which I am writing A2, B2, C2, these are all capital letters because these are belonging to high voltage side. So the terminals belonging to high voltage side will be written in capital letter. So since it is delta connected, high voltage side is delta connected, so I will draw 3 windings, 3 phase windings like this. This is your delta connected. Now we all know that a winding has got 2 terminals. I mean to say, if there is a terminal A2, there will be terminal A1. So for the phase A winding, there will be 2 terminals, A2 and A1. For the phase B winding, there will be 2 terminals, B2 and B1. For the phase C winding, there will be 2 terminals, C2 and C1. But right now we will not write the other terminals, that means A1, B1, C1. We will wait. Why we are going to wait, I will let you know why we are going to wait. The reason will be clear shortly. So what I will be doing is that I will be copying this particular diagram. It will be of help to us. So let me copy this. So now over here what we will do is that we will draw the low voltage side, that means LV side. Now how we are going to draw the LV side? The LV side will be drawn by pointing the phase A arm towards 11 o'clock, because you see what's the time in the clock, 11 o'clock. So low voltage side phase A winding will be pointing towards 11. So let me show it over here. I am pointing the low voltage side winding towards 11 like this. So this is your terminal A2. This is your terminal A2. Now where we will plot, where we will show B2 and C2, we will find it out shortly. Let me first draw the 3 windings of the star connection which is belonging to low voltage side, that is LV side. Now one more thing can be noticed here is that I have written the terminal A2 in small letter, as it is belonging to LV side. This is belonging to LV side, so it has to be in small letter, and this thing was belonging to HV side, so it has to be in capital letter. Like this, it has to be in capital letter. Now where will be B2 and C2? So we can do one thing, is that we will find like this. Let's say we have got 3 phasors like this. Let's say we have got 3 phasors like this. Now we are naming these phasors. Let's say this is a phasor OA, OB and OC. They are having a angle of 120 degree between them. They are having an angle of 120 degree between them. 120 degree. Now what you can think is that, let's say there is an observer. There is an observer standing here. So this is the observer. This is the observer standing here. And let's say these phasors are rotating in this anti-clockwise direction. And also you have to just remember that this 3 phasors OA, OB, OC, they are fixed at point O, as if the whole thing is pivoted around point O. The whole thing is pivoted around point O and the thing is rotating. So what will happen? Phasor, the observer will see first OA, then 120 degree later the observer will see OB, then another 120 degree later it will see OC. So based on this logic, we can say that if you are having A2 here, so if this thing is rotating in this way, so you should have B2 here, you should have C2 here. You can just compare with this one, because the phase sequence is ABC. The phase sequence is ABC. So the observer should see first phasor OA moving past him or her. Then after 120 degree later, the observer should see moving past him or her phasor OB, then another 120 degree phasor OC, because these 3 phasors OA, OB, OC, they are made in such a way that it is rotating as a cohesive unit. I mean to say, this point O is fixed, it is not moving anywhere, it is not going anywhere. Point O is fixed and this thing is rotating. You can just for convenience think of some 3 metallic rods. Let's say there are 3 metallic rods and the 3 metallic rods are welded at point O. The 3 metallic rods are welded at point O. Now if you just press the point O and rotate this thing in anti-clockwise direction, this will rotate in such a way that first OA is coming at this position, then OB, then OC. Now while drawing this diagram, a very important, so I am erasing this portion. This is not needed. It was just as a side explanation, so that we are confidently able to determine that where we will write small b2, small c2, because you remember we have initially started with writing small a2. Small a2 means the low voltage side terminal, small a2, and since in the connection it is written dy11, so obviously the time in the clock is 11 o'clock, so LV side should point towards 11, and you can see here HV side is pointing towards 12 actually. If I just also bring this, let me bring it, let me make it somewhat smaller so that it will fit. So we will see also that here also actually that kind of thing is going on. Let me show you. So if I just do once more a copy like this, so no, let me undo it. Let me do one thing, let me draw the clock once more. So I am drawing the clock position like this. So you can see this thing is actually pointing towards 12 if you draw some imaginary line passing through the vertex A2. Let's say we are writing here 12, so this is your 12th position. So you can see this is pointing towards 12, this thing is pointing towards 12. Now this is some imaginary kind of thing, so I am showing it by dotted line. Let me show it by a dotted line. So you can see this one is the thing which is pointing towards 12. If I highlight this, you can see this thing is pointing towards 12. Okay, so this was your HV side, and LV side is also, you can see LV side is also pointing towards 11 because it's 11 o'clock. Now you can compare to this diagram, really it will be easier for you. You can compare it like this, not this one, really this one. You can see here LV side, here the LV side is actually pointing towards 11 and HV side was pointing towards 12. So that thing is we are repeating here. Here LV side is pointing towards 11 and HV side, there, let me draw this thing is pointing towards 12. Now recall that at the time of writing the terminals of the HV side, that means capital A2, capital B2, C2, I have not written the other terminals, that means A1, capital A1, I mean capital B1, C1, and I have told at that time there is a reason for that. So now it is evident why I have not written. You see, the phase windings on the HV side and LV side, they should be always drawn parallel to each other. This is very important. Whenever we are drawing the phasor group connection for a three-phase transformer, it is very important thing to remember that the phase windings on the high voltage side, this is our HV side, that is high voltage side, and this one is our low voltage side. So you see, the phase winding on the HV and LV side, they should be drawn parallel to each other. If I just want to indicate like this, you can see these two things should be parallel, these two windings should be parallel. So if these two windings has to be drawn parallel, then you can see that if this is your A2, then this one will be your A1. So obviously on this side A1 will be this one will be A1. Likewise, you see these two windings should be parallel, these two windings should be parallel. These two windings should be parallel. Okay, so if this is your capital B2, this is your small b2, because it is belonging to LV side, this is HV side. But if this is B2, this will be B1, and likewise on the LV side this will be B1. Likewise, this is your C2, this is your C2. So you can see these two sides should be parallel, these two sides are parallel, this one and this one, they should be parallel. So this is C2, this will be your C1, and on this side also this will be your C1. So this is very important thing we should remember, that whenever we are drawing the phasor group connections for a three-phase transformer using the clock method of designating the angles, the phase difference or the angle between the line EMF of the HV and LV side. Then when we are drawing the connection diagram, we should always make sure that the windings, the phase windings on the HV and LV side are drawn parallel to each other. The way it is shown here, capital A to capital A1 is parallel to small a to small a1. So capital A to capital A1 means HV side phase A winding, and small a to small a1 means LV side, low voltage side, phase A winding. The way it is shown here. The same thing goes for phase B and C. Now after showing this, we need to demonstrate really that there is indeed a phase difference of 30 degree between the LV side and HV side line EMF. You can see here it is written 11 o'clock. Now just merely saying there is a phase difference of 30 degree is not going to satisfy many of us, because it is leaving the question of whether leading or lagging thing, how it will be covered. So this dy11, the connection which we are drawing, dy11 is actually connection belonging to phasor group 4. Okay, it is belonging to phasor group 4, where we are having 30 degree lead. Now how to figure out this meaning of 30 degree lead? Now recall that in the beginning itself it was said that minute hand is fixed at 12 o'clock position. So this means that HV side line EMF should be treated as the reference. Okay, so since we are saying minute hand is fixed, we are saying that minute hand is fixed at 12 position. So we will take this thing as what? We will imply this thing as HV side line EMF, HV side line EMF is chosen as reference, So because the basic justification we can find out is that it was said that minute hand is fixed at 12 o'clock position. So since minute hand is fixed at 12 o'clock position, so that is the reason we are saying that high voltage side line EMF is chosen as reference. So HV side is our reference. So when we are saying 30 degree lead, obviously it is the LV side line EMF which is leading, because HV side in any case we are making the high voltage side line EMF as the reference. So obviously the 30 degree lead means that the LV side line EMF is leading by an angle of 30 degree. And why it is leading, not lagging or like that kind of thing, let us just apply one what should I say, memory aid. Okay, memory aid. If you just think in terms of time, first what is going to come? 11 o'clock will come first. After 11 o'clock 12 o'clock will come. So obviously 11 o'clock thing is leading the 12 o'clock, because if you consider in terms of time, first 11 o'clock happens, then 12 o'clock happens. So in that way you see LV winding, this is our hand is your LV winding. So this LV winding is pointing towards 11. LV winding is pointing towards 11, or LV winding line EMF, LV winding. I am writing WDG as the short form for winding. LV winding line EMF is pointing towards 11, and 11 o'clock comes earlier, 12 o'clocks come later on, and HV side line EMF is pointing towards 12. So that is the reason we are saying it is 30 degree lead. Now let us demonstrate that whether actually it is 30 degree lead or not. So for doing that, what we will do, we will again just draw that thing quickly. Let me draw it in quick succession, or rather we can do one thing. Okay, let me draw it, that will be easier, because it is some sort of recap which will happen. So let me align this. So we can copy this once more because we will be requiring this thing at two places. Now let us extend it. So we had started drawing the high voltage side by drawing three vertices as if they are the vertices of an equilateral triangle, and the three vertices will be named as A2, B2, C2, starting from the top A2, then moving in clockwise direction, that means here B2 and then C2. And we have drawn the windings like this because the high voltage side was delta connected. The capital D was suggesting that capital D, capital letter stands for high voltage side, and with a purpose only we have not written down the other terminals of phase A, that means A1. We have written only A2. Likewise, we have not written the other terminal of phase B, that means B1 we have not written, we have written only B2. The same thing goes for phase C. The reason being told was that it will be completed, the other terminal markings of HV side like A1, B1, C1 will be completed after we have drawn the windings on the LV side, that means low voltage side. Now here you can see that high voltage side is actually pointing towards 12 o'clock position. You can see this thing is pointing towards 12 o'clock position. And if I just write here the dial of the clock like this, so this is 12, this is 11. So phase A LV side, phase A LV side will be pointing towards 11. We will be pointing towards 11 like this. And yes, let me write what we are doing. We are drawing the phasor group connection for DY11. We are drawing the phasor group connection for DY11 like this. So obviously there will be three windings. It is a star connected. Now we are saying what? That terminal A2 is pointing towards 11. So you can notice one more point is that on the HV side, that means high voltage side, on the high voltage side also we are starting with the terminal A2. Terminal A2 is pointing towards 12, and you can recall here that in the diagram HV side line EMF is pointing towards 12. So that way, although it is not line EMF, but it is pointing towards 12. This dotted, this green line which is not dotted yet. So let me make it dotted. So this one is your pointing towards 12. Likewise on the LV side, on the LV side also you can see phase A winding is pointing towards 11 because it is DY11. So this is your LV side. Likewise we will draw phase B2 and we will draw phase C2 like this, phase C2. So obviously these two sides will be parallel to each other. These are parallel to each other. So if this is your capital A2, this is your small a2, so this will be your small a1. So already on this HV side this will be your small a1. Likewise you can see this one and this one, they are parallel, so here also we can write this is your small b1. So obviously on the HV side this will be your capital B1 because it is HV side. And the same thing, I am not drawing it another way so that it will get clumsy, but this phase C2 and C2 will be parallel. If you want you can highlight this one, and this one will be parallel. So that way you can write here this will be C2, so this will be C1 and this will be small c1. Now one important point we should remember is that while making the connection, the polarity of terminal A1, B1, C1, I again repeat it, the polarity of the terminal A1, B1, C1 on the LV side must be having the same polarity. Then only we can join them together to form the star point or the neutral point of the LV side, because if you are having 2 points which are having a different electrical potential, you cannot short them or join them together. If you are connecting 2 points together, then we should make sure that those 2 terminals which are joined together, they are having same potential, same electric potential. So that way I am saying that terminal A1, B1, C1, they should have the same polarity, they should have the same polarity. So prior to doing this connection, we should check the polarities of the terminals, and then only we are able to make the connections. Those terminals which will have the same potential on the low voltage side, LV side, will be connected together to form the star point on the neutral point A1, B1, C1. Now what I was actually mentioning earlier was that we need to demonstrate, because you remember in the beginning it was said that the line EMF of the HV and LV side, they will be differing by a phase of 30 degree. Of course the LV side line EMF will be leading the HV side by angle of 30 degree, because it's 11 o'clock, and at 11 o'clock position you can see the hour hand and the minute hand. So hour hand, minute hand are having a difference of 30 degree. So these are basically representing the LV side line EMF and HV side line EMF. So they are differing by 30 degree, and also we have stated the reason why it will be 30 degree lead, because minute hand is fixed, which is actually representing the high voltage side line EMF. So obviously your what should I say, the HV side line EMF is chosen as the reference, HV side line EMF is chosen as the reference. So now we will do what, we will make this thing actually a bit smaller, so that we are having sufficient space. So I will be making it smaller. Let me make it smaller. So if we want to make it smaller, we want to keep this thing in front of our eyes, but at the same time we have to demonstrate few more things based on this. It is there in front of the eyes, though it's better for us, so that is the reason it is kept like that. So now do one thing, we have to demonstrate they are differing by 30 degree. So let us do one thing, let us take the line voltage of the HV side like B2C2. So we are taking the line voltage of the HV side like this. This is your B2, this is your C2, this is coming from here, straight from here, you can see this thing, okay, B2 C2. So this is your HV side line EMF, HV side high voltage side line EMF, or you can say line voltage, line to line voltage, HV side. Likewise on the LV side also we should select B2C2. So what is your B2C2 phasor? This B2C2 phasor is this one, this phasor is your B2C2. So this phasor is your B2C2. So let us draw like this parallel to this. So this is your B2, this is your C2, and this is your LV side line EMF or line voltage. So just to keep the parity, we will not show these windings here, we will simply indicate the phasor. So let me indicate the phasor, that way it will be better. So this is your C2 and B2. Now we know that phasors can be moved parallelly from one place to another place. So you can see this phasor B2C2 has been moved from this place to this place, but only condition which we need to keep is that the phasors can be moved from one place to another place, but provided the movement is made parallel, it should be moved always parallelly. Here also you can see that B2C2 was moved from this position, B2 C2 was moved from this position to this position, so it was moved parallelly. Here also it is moved parallelly, like that. So we can move the phasors from one place to another place, but the only criteria is that it should be moved parallelly. Okay, so we have to keep it parallel while we are moving it. So now we can either join capital C2 with small c2 or capital B2 with small b2, so that we actually get the idea. What kind of idea? That actually the line voltages on HV and LV side, they are having a phase difference of 30 degree or not, because we are doing the phasor group connection for DY11. So you can join either capital C2 with small c2 like this. Let me encircle this one. So you can either join this capital C2 with, you can either join this capital C2, you can either join this capital C2 with small c2, capital C2 with small c2 like this. You can join it together, or you can join this capital B2. Let me use some another color. Let me use blue color. You can join capital B2 with small b2. So you can choose any of either you join capital B2 with small b2, or you join capital C2 with small c2. You can join it. So let me join C2 with C2. So I am joining that way. So we can actually just move it further a little bit. So I am joining this one. So this is your C2 B2, and we can move the phasors parallelly. You can remember that the only condition is that they can be moved parallelly from one point to another point. So we have to maintain that very strictly. So this is your small c2, small b2. This is LV side line EMF. This is LV side line EMF. And likewise you have got capital C2 and capital B2. This is HV side line EMF, HV side line EMF, and the angle between them will be 30 degree, because we can just find a small calculation here. You can see this is a, let me zoom it. You can see over here I am just placing this B1 somewhere else. Let's say I'm placing it over here. Let me place B1 over here. So you see here, this angle is actually 120 degree, right? This angle is 120 degree. This angle will be, these two angles are equal, so this will be 30 degree, this will be also 30 degree, right? So now if I just make the comparison of this one with this one, you see here. So if I draw a line, let's say I am drawing a line like this, I am drawing a line, let me use some another color. I am drawing a line like this. I can draw the line like this, isn't it? Let me do one thing. Let me bring this a little bit smaller portion like this. So now let me just erase this portion. These are not needed now. It was shown earlier to indicate these phase windings on the HV and LV side will be parallel to each other. Let us not keep those things now. We just want to prove that it will be 30 degree the angle. So now you just take this line. So this is this one, and this angle is how much? This angle is 30 degree. If I just zoom it, you can see this was your B2C2, this was your B2C2 small side, and this angle is your 120. This one will be your 30 degree. So that is what is shown there. You can find it out here. This angle is 30 degree. Now again you apply that same thing. Let me keep this thing a little bit aside like this way. Let's say I am placing this thing over here. So if you again just place one observer over here, you are placing one observer over here. Okay, he is the observer. And this entire thing is rotating in, say, anti-clockwise direction. So what will happen? The observer will see first L.V side line EMF C2B2, and after 30 degree the observer will see the H.V side line EMF, H.V side line EMF, that means capital C2B2. Because again you have to think in this way. Let me mention it over here separately. What is this one? This one is your C2 B2, and this is your capital C2 B2. So this thing is fixed. This point is fixed. This point is fixed, and making this point fixed, the entire thing is rotating like this. So obviously L.V side line EMF will come first towards the observer, and after 30 degree rotation the H.V side will come. So the observer is going to see the L.V side, that is low voltage side line EMF small C2B2 first, and 30 degrees later on the observer will see the H.V side line EMF, H.V side line EMF, that means capital C2B2. So that is the reason we are saying it is the L.V side line EMF which is leading the H.V side by an angle of 30 degree, which I have suggested in a memory aid way, that first 11 o'clock comes and after that 12 o'clock is coming. So whoever is pointing towards 11 will be leading, and whoever is pointing towards 12 will be lagging. Okay, so this was the phasor group connections. Now regarding the connection, one more thing which I have mentioned earlier, again I am saying that the terminals which we can see here, let me zoom it, the terminals A1, B1, C1, this should have the same potential, or they should have the same polarity. Then only we can connect them, join them together. Otherwise we cannot join them together if the terminals A1, B1, C1 are having different polarity. So it is very important to perform the polarity test of the three-phase transformer terminals before making the connections. Usually on the transformer nameplate side, the polarity markings will be mentioned, like say capital A1, capital B1, capital C1 will be having same polarity because all of them are having suffix 1, and likewise small a1, small b1, small c1 will have same polarity because they are having suffix 1. But if you are connecting a bank of three-phase transformer, that means you are connecting three separate single phase transformer, you are having 3 units of single phase transformer, you are connecting them to work as a three-phase transformer, which we are calling as bank of three-phase transformer. So bank of three-phase transformer means that when we are connecting together 3 single phase transformer units to work as a three-phase transformer, we call that as bank of three-phase transformer. So in those cases it is important that you make sure about the polarity. Now as far as the delta connection is concerned, you can see in delta connection what happens. The start of one is getting connected with the finish of the other. Like here you can see, let me show in a better way. I am zooming it. You see capital A2 is connected with C1. So if you take the terminal 1 as the start, terminal 1 means I just want to make this statement that if the suffix is 1, if the suffix is 1, so let's say it is the start, and if the suffix is 2, then it is the end. So C1, 1 suffix is means starting, and A2, 2 suffix means it is the end. So start is connected with end. Start of phase C is connected with terminal A2, that means end of phase A. Likewise you can see here capital A1 B2. So suffix 1 means start, suffix 2 means end or finish. So start finish, you can see suffix 1 suffix 2 connected, start finish, again start finish, again B1 C2 means start finish. And there is one interesting thing you will get to know is that if your delta connection is correct, you know, then the sequence in which the suffix are appearing, they will be always same if you are taking in a clockwise way. Let me just bring this one, copy this one once more. I am only taking this portion. Let's say I am taking this portion. So now you will see that over here you write this one in cyclic order. Let's say A, B, C. So you have to move it in cyclic way. So what is this cyclic way? First is A, B, then if you move in cyclic way, then it is your B, C. Again you move in cyclic way, then it is C, A. So you just watch out for A, B. Now I will be writing in, let's say, capital. So say for A, B, what is the suffix order? A, B, it is your suffix order is, I am writing in a different color to draw your attention. Suffix order is 1, 2. What about B, C? B, C, suffix order is again, if you can see, B, C is 1, 2. Then what is the next thing is your C, A. So for C, A, what is the suffix order? Again it is 1, 2. So you see, we have found that if you are writing these terminals A, B, C in a cyclic fashion, the way it is shown here, A, B, B, C, C, A, then the order of the suffix will come as same. For A, B, the order of the suffix is, you see, 1, 2. Why? Because it is A1, B2. So order of the suffix is appearing in 1, 2. Then it is your B, C, it is again coming in order B1, C2. So 1 and 2. So that way also you can check, or you can simply check that start and finish are connected or not. For the delta connection, start and finish, start and finish. So in a sense you can see that the polarity of terminal C1 and A2 are not same, they are opposite. Likewise the polarity of terminal A1 and B2 are not same, but this is your delta connection, this is your delta connection. So for delta connection, this is the way we are connecting it. So this is your delta connection. But in case of star connection, as I have said earlier, again I am saying that the polarity of the terminals A1, B1, C1, the polarity of the terminals A1, B1, C1 should be of same potential, or they should have the same polarity. Okay, now as far as the connection is concerned, we have already shown here which winding will be connected in which way. So if you want, you can further indicate it like this. Let me use it. So let's say I am drawing the 3-phase windings like this. I am drawing the 3-phase windings. So this is, let's say I am writing here A2, then I should write here B2, then I should write here C2, then obviously A1 is here, B1 is here, C1 is here. Now the same thing I am going to do for phase LV side. This was your HV side, now LV side. So LV side also. Now let me take this thing somewhere. Let's say I'm taking this somewhere. So we are again drawing the LV side. So this is your A2 A1, this is your B2 B1, C2 C1. So you see the terminal A2 and A2 are facing each other from the HV and LV side. Likewise the terminal B2 from HV side is facing terminal B2 from LV side. Now you can make the connection. You can see A2 is connected with C1 here. Let me zoom it if you can figure it out easily. So you can see here that A2 is connected with C1. So A2 is connected with C1. So here also we will connect A2 with C1. So A2 and C1 should be connected together. A2 and C1, it should be connected together. A2 and C1. Like this. What else is there? A1 and B2 are connected. So we will connect A1 and B2. A1 and B2. A1 and B2 are connected. What else? Let us see once again. A1 and B2, then B1 and C2. B1 and C2 are connected. You can see B1 and C2. So B1 and C2. B1 and C2. So this is B1 and C2, like this. And what about the LV side? LV side is very straightforward. You will short the terminals A1 B1 C1 together because they are having same polarity, A1 B1 C1. So we will short A1 B1 C1 together. They are having the same polarity, and this will be treated as the neutral side of the LV side, that is low voltage side. So this will be treated as, this thing will be treated as small n. Small n means the neutral side. Okay. So in this way you can make the connections work for you, and in the lab if you are making this connection, then you can only measure whether the difference is 30 degree or not, but for leading lagging you have to use a power oscilloscope. Otherwise you don't have any option of figuring it out except for the connection. You can always take the help of these connections which are shown here. By this connection you can always show it. Now one question may come to the mind of the reader is that why it was told that we have to keep the phase windings parallel to each other the way it is shown here. Phase A2 and here A2 A1 of LV side and LV side, HV and LV side, actually HV and LV side, these two windings were said to be kept parallel to each other, isn't it? So why they should be parallel? So the reason for this is that the induced EMF on the HV and LV side of phase A will be in same phase because the windings are mounted on the same limb. Now in order to demonstrate this, then I need to draw the three-phase transformer schematic diagram. I will draw it in a quick succession. I will not elaborate that much. Let us draw one three-phase transformer core, because that is an important question which can come to the mind of the viewer, why it should be drawn parallel. So let me draw a core of a three-phase transformer. So we all know that transformer core is laminated, so it will be laminated, but I will show few laminations. I mean to say it's not possible to indicate that much of lamination, but still I will indicate it that yes, the transformer core is laminated. transformer core is laminated. And this is a 3-leg transformer. You can have cases where you're having 5-leg transformers also. So the 3 limbs of the transformer will be like this. This is the 3 limbs. Now let us do one thing. Let us, this thing is known as your transformer window, and these are the limbs. The upper portion, this thing is your yoke. Now as said, these are your laminated structure. These are your laminated structure. So I should be showing like this. These are all your laminated, because in order to reduce the eddy current losses, the transformer core is laminated. And for reducing the hysteresis loss, we are making the use of CRGO, that is cold rolled. CRGO means cold rolled grain oriented silicon steel. So these are the 3 limbs. Okay, these are the 3 limbs. So let me write the portions quickly. This thing is known as yoke of the transformer. This is also yoke of the transformer, and this thing is your limb, or you can call leg, L-I-M-B, limb, L-I-M-B, limb. You can also call it leg. So what is happening in this thing? Basically the windings are wound around this thing, this 3 limbs. So let me copy this. So we will be placing the H.V side and L.V side windings on these 3 limbs. There are 3 limbs because we have got 3 phases, so that is why we have got 3 limbs. So we will be placing the H.V and L.V side of phase around this limb. So on this limb what will be placed? H.V and L.V winding, H.V and L.V winding. I am writing WDG as the short form for winding. On this limb, H.V and L.V winding of phase A, phase A will be placed. Likewise, on this limb, what is going to be placed? On this limb, HV and LV winding, HV and LV winding. I am writing WDG as the short form for winding of phase B, and obviously lastly it is needless to say, but still we are writing on this limb what we are going to place? HV and LV side, HV and LV side, HV and LV winding. Let me write windings because I am writing winding. HV and LV winding, I am writing WDG as the short form for winding. So on this limb, HV and LV winding of phase C, it has to be placed. So now you see on this limb, if you are placing the high voltage and low voltage winding of phase A, so obviously they are going to link the same flux. The same flux will be linked by both the windings. This is your flux, let's say phi A. So both will link the same flux. The same logic holds for this one. This will be having your flux phi B here. Not here actually exactly. On this limb I am focusing this one, phi B. And likewise you will have here phi C. So that is the reason it was said that the windings on the HV and LV side should be drawn parallel to each other, because you see both high voltage and low voltage winding, both high voltage and low voltage winding for both for all the three phases A, B, C, they are mounted on the same limb. Or like you can see on this limb, high voltage and low voltage winding of phase A is going to be wound. So obviously the phase EMF or the phase induced EMF will be in same phase, because they are mounted on the same limb. The same thing goes for here. That is the reason we have shown. So this is the basically the reason. So let me do one thing. Let me make this thing a little shorter. So this is basically the reason behind that thing. Let me bring up this particular thing. So if you want, you can just have a correlation why it was said that it should be drawn parallel to each other, why it was said that this should be drawn parallel. This is the basically reason. Okay, they should be parallel. This is the reason. This is the reason for that. This is the reason for this, that they should be drawn parallel to each other. Okay, so thank you for joining with me. Goodbye.